They are the strangest stars in the universe, magnetars, pulsars, and neutron stars. Born from stellar death, they twist space-time and physics itself. What secrets do these cosmic enigmas still hide? In this journey, we'll explore their extremes and mysteries. If you enjoy it, please like, subscribe and share, and tell us in the comments which of these stars fascinates you the most and why. Thank you for watching. Now let's begin. The final stage of a massive star's life arrives when the nuclear reactions that once sustained it can no longer produce enough energy to resist the inward pull of gravity. For most of its life, such a star burns hydrogen into helium, and then in later stages helium into heavier elements like carbon and oxygen. In the larger stars, the process continues through a chain of elements until iron builds up in the core. Iron does not release energy when fused into heavier nuclei. Once the central regions of the star become dominated by iron fusion, cannot provide the outward pressure that had kept the star stable for millions of years. The core grows dense and hot, but without a new energy source, the balance tips. Gravity overwhelms pressure, and the collapse begins. The collapse of the iron core happens with extraordinary speed. In less than a single second, the central region shrinks from thousands of kilometers to a sphere barely tens of kilometers across. During this contraction, protons and electrons are squeezed together so tightly that they combine to form neutrons and neutrinos. The process is called neutronization, and the neutrinos stream outward in vast numbers. A single core collapse releases more neutrinos in a matter of seconds than our Sun will emit in its entire 10 billion year lifetime. Most of these neutrinos pass through matter almost unhindered, but the density of the collapsing star is so high that they briefly interact with surrounding layers, depositing some energy. This energy helps drive the shock wave that becomes the outward explosion known as a supernova. While the outer layers are blasted into space, enriching the interstellar medium with heavy elements, the collapsed core remains behind. That core is now so dense that nearly all its particles are neutrons packed together in a state of matter found nowhere else. This object is the neutron star. The neutron star forms with properties that push the boundaries of physical understanding. Its radius is typically about 20 kilometers, yet it contains more mass than our Sun. That means the matter inside it is compressed to densities exceeding those of atomic nuclei. The surface gravity is immense. A person standing on the surface, if such a thing were possible, would feel a gravitational pull billions of times stronger than on Earth. Light trying to escape is bent by the intense curvature of space-time. These effects are not merely theoretical. They are supported by precise astronomical observations of neutron star behavior. In the earliest moments after birth, the neutron star may be extremely hot, with temperatures in the hundreds of billions of degrees. It cools rapidly as neutrinos continue to carry energy away. Within a few years, its temperature falls to millions of degrees, and it emits light mainly in X-rays. Over longer timescales, its surface cools further, but it remains a source of high-energy radiation for hundreds of thousands of years. The violence of the supernova and the rapid collapse impart the neutron star with rapid spin. Just as a spinning skater turns faster by pulling in her arms, the collapsing core turns faster as its radius shrinks. A core that rotates once every day can turn several times each second as a neutron star. This rotation, combined with intense magnetic fields inherited from the progenitor star, becomes central to much of the behavior astronomers later observe. The surrounding environment also bears traces of the collapse. The expelled outer layers of the star expand into space as a supernova remnant a shell of gas and dust energized by the explosion. These remnants are observed with telescopes across the electromagnetic spectrum from radio waves to gamma rays, and they provide a visible marker of where a neutron star may lie hidden inside. The Crab Nebula, born from a supernova seen on Earth in the year 1054, still glows today with a pulsar at its centre. For the neutron star itself, conditions are unlike any terrestrial laboratory. The pressure is so high that atomic nuclei can no longer remain separate. Instead, neutrons dominate and the material behaves according to the rules of nuclear physics under extreme compression. This is the origin of the name neutron star. Yet despite their name, neutron stars are not made solely of neutrons. Protons, electrons, and possibly other exotic particles may be present in varying proportions, especially toward the inner core. Understanding the balance of these components remains a central research question. Astronomers identify neutron stars through several observational signatures. Some reveal themselves as pulsars, their radio beams sweeping across Earth in precise rhythms. Others appear as isolated sources of X-rays, or as companions in binary systems where they accrete material. In each case, the foundation of their existence traces back to the collapse of a massive star's core in a supernova. This transformation converts a luminous giant into a remnant smaller than a city, yet containing more mass than the Sun. The process also plays a role in cosmic chemistry. The outer layers expelled during the explosion carry elements like oxygen, silicon, and iron into space-seeding future generations of stars and planets. The heavy elements that make up planets and living bodies originate in such stellar deaths, though the focus here remains on the remnant itself. The balance between the forces at work is delicate. If the core remnant has too much mass, even neutron pressure cannot hold back gravity. In that case, collapse continues until a black hole forms. Observational data suggest that the upper limit for a neutron star's mass is somewhere between 2 and 3 times that of the Sun. This limit continues to be refined as new measurements become available. For cores below that threshold, neutron stars remain stable for millions of years. From the calm distance of Earth, the sequence from massive star to supernova to neutron star is followed through telescopic surveys and theoretical modeling. Every step is supported by observations from the light curves of supernovae to the detection of neutrinos from the collapse of supernova 1987A, which provides direct evidence for the processes described. These detections confirm that neutrinos carry away most of the energy released during collapse, and that the newly formed object traps matter at densities beyond nuclear scales. A neutron star once formed in the aftermath of a supernova can be understood in layers that begin at its outer surface and extend inward to depths where matter takes on unfamiliar forms. At the surface there exists a thin atmosphere only a few centimeters thick. Despite its small size, this layer regulates the radiation escaping into space. It is composed of light elements such as hydrogen and helium, if these are present, though over time heavier elements may dominate if lighter ones are stripped away or consumed. The radiation that emerges from this surface is shaped by the gravitational field of the star, which bends light paths and shifts photon energies. Below the atmosphere lies the solid crust. This crust is only about 1 kilometer thick, but contains a wealth of physical processes. In the outer crust, the density gradually rises to values, where atomic nuclei are arranged in a lattice surrounded by a sea of electrons. The nuclei at these densities are highly neutron-rich, containing more neutrons than stable elements on Earth. As one moves deeper, the density increases further, and neutrons begin to leak out of the nuclei, forming a gas that permeates the lattice. This region is known as the inner crust. The balance of forces in the crust gives it remarkable strength. Calculations suggest that the crystalline lattice may be the strongest material in the universe, able to withstand stresses far beyond those of any terrestrial solid. This strength becomes important when stresses accumulate in magnetars, and lead to crustal fractures. Beneath the crust lies the mantle and the outer core. Here the densities surpass those found inside atomic nuclei, reaching several times nuclear density. In this environment, neutrons dominate, but a fraction of protons and electrons remain to maintain charge balance. The interactions among these particles determine many of the star's macroscopic properties, including its heat transport rotation behavior and magnetic field evolution. The outer core may also host exotic states of matter, such as superfluid neutrons and superconducting protons. In a superfluid, particles move without viscosity, and in a superconductor, electric currents can flow indefinitely without resistance. Evidence for these states comes indirectly from observed pulsar glitches and from theoretical modeling, but their exact character remains uncertain. Deeper still is the inner core, the most mysterious region. Here the pressure is immense and the density may be 5 to 10 times greater than nuclear density. Several possibilities have been proposed for the matter present in these depths. One option is that it remains primarily neutrons with some protons and electrons. Another is that more exotic particles appear, such as hyperons containing strange quarks. Some models even suggest a transition to deconfined quark matter, where quarks are no longer bound inside protons and neutrons, but move freely in a dense soup. Current observations are not yet able to distinguish between these possibilities, and this question represents one of the central uncertainties in modern astrophysics. Between the inner crust and the outer core lies a transitional zone where nuclear structures deform under extreme pressure. In this region, matter organizes into unusual shapes sometimes referred to as nuclear pasta. Instead of spherical nuclei, one may find sheets rods or other complex geometries formed by the competition between nuclear attraction and Coulomb repulsion. These structures affect how the crust conducts heat and how neutrinos pass through the star, influencing cooling rates. The study of nuclear pasta has become an interdisciplinary field, connecting nuclear physics, astrophysics, and computational modeling. Each of these layers contributes to the overall behavior of the neutron star. The crust determines how stresses build and how starquakes occur. The outer core controls rotational dynamics and magnetic field evolution. The inner core sets the maximum mass and stability limit. Together, they produce an object with properties so extreme that they challenge current understanding of physics. Observational evidence for these internal structures comes from several avenues. The cooling of young neutron stars as measured in X-ray observations provides clues about how efficiently neutrinos escape from the core. Rapid cooling in some stars suggests the presence of enhanced neutrino emission processes, which depend on the interior composition. Pulsar timing observations reveal sudden glitches which are interpreted as interactions between the crust and the superfluid interior. In addition, gravitational wave measurements from neutron star mergers are beginning to provide constraints on the stiffness of dense matter, described by the equation of state. Each data point narrows the range of models but does not yet provide a definitive picture. The surface of a neutron star also reflects its interior. Observations in X-rays show hotspots where magnetic fields channel heat. The spectrum of radiation depends on surface composition, whether dominated by hydrogen, helium, or heavier elements. In some cases, absorption lines may provide direct measurement of surface conditions, though these measurements are challenging and require high-precision instruments. By combining observational data across different wavelengths and from different phenomena, astronomers gradually build a picture of what lies beneath the surface. Theoretical models must reconcile these constraints with known physics of nuclear interactions. Experiments on Earth using particle accelerators can reach densities similar to those of atomic nuclei, but not the extreme densities of neutron star cores. Thus, neutron stars serve as natural laboratories, offering the only environment where such conditions exist. The equation of state, which relates pressure to density, is a central piece of the puzzle. A stiff equation of state allows a neutron star to support more mass before collapsing into a black hole, while a soft equation of state predicts a lower maximum mass. Observations of massive neutron stars near two solar masses have already ruled out many soft equations of state, but uncertainties remain at higher densities. Gravitational wave signals from mergers provide another path forward, as the tidal deformability of each star during collision depends on its equation of state. The distribution of matter in layers also affects magnetic field behavior, the conductivity of the crust, the presence of superconductivity in the outer core and possible exotic states in the inner core all shape how magnetic fields evolve over time. Some stars retain fields of 1 trillion Gauss for millions of years, while others decay more quickly. Understanding these processes requires integrating the microphysics of particles with the astrophysical timescales of stellar evolution. The journey inward from the surface to the core of a neutron star is therefore a journey across physics itself, from familiar solid states to the edge of quark matter. Each layer is linked to observable consequences, and each is under active study through a combination of theory, simulation, and observation. What begins as a collapsed stellar core becomes an object of layered complexity, where matter organizes itself in forms dictated by density, pressure, and fundamental forces. As one moves deeper into the structure of a neutron star, the arrangement of matter begins to take on shapes that are neither familiar solids nor simple liquids. In the region between the crystalline crust and the more uniform fluid core, nuclear matter organizes itself into exotic structures that scientists have named nuclear pasta. The name reflects the resemblance of these shapes to everyday forms such as sheets, tubes, and bubbles, though the comparison is only a convenience for description. At the densities present in this zone, roughly 1/10 to 1/2 of nuclear density, the competition between nuclear attraction and electrical repulsion leads to geometries that minimize energy in unusual ways. Instead of discrete spherical nuclei packed in a lattice, one finds elongated rods that extend across regions like spaghetti flat sheets that resemble lasagna, or bubbles of void within nuclear matter that look like Swiss cheese. These forms are not decorative but arise naturally from the balance of forces under conditions of extreme pressure. The presence of nuclear pasta has important consequences for the physics of neutron stars. The arrangement of nuclei affects how heat is transported through the crust. In a crystalline lattice, heat can flow in certain patterns, but in pasta structures the pathways change, altering thermal conductivity. This in turn influences how the surface of the neutron star cools, and how quickly hot regions spread their energy. Observations of cooling neutron stars, particularly those seen after periods of accretion in binary systems, provide indirect evidence for the properties of the crust and inner layers. Another role of nuclear pasta lies in its effect on neutrino scattering. Neutrinos are the main carriers of energy out of a young neutron star. The way they interact with matter determines cooling rates in the first million years. The complex structures of the pasta phase increase the cross-section, for scattering, meaning neutrinos are more likely to interact rather than escape freely. This slows cooling and leaves measurable signatures in the thermal evolution of stars. Theoretical models predict these effects, and astronomers compare them with data from X-ray observatories to test the presence of pasta. The mechanical properties of nuclear pasta are also striking. Calculations suggest that these structures may be even stronger than the crystalline lattice above them, forming the strongest known material in the universe. This strength becomes relevant when stresses build up in magnetized stars. As magnetic fields twist and evolve, they press against the solid crust and the pasta layer beneath. When the stress exceeds the yield strength, the crust fractures in what is known as a starquake. These events release energy observable as sudden changes in rotation or bursts of high-energy radiation. The pasta layer may act as a buffer, storing and releasing energy on timescales longer than those of the outer crust alone. The study of nuclear pasta requires large-scale computational simulations because no laboratory can reproduce the conditions of density and pressure present in neutron stars. Physicists use methods from nuclear theory and condensed matter physics to model thousands of nucleons interacting under these extreme conditions. Supercomputers are employed to calculate the arrangement that minimizes energy. The resulting simulations show regular patterns emerging spontaneously, confirming that pasta phases are a natural outcome of the forces at play. Observationally direct proof of pasta is not available, but indirect evidence grows stronger. The glitches in pulsar rotation thought to be caused by interactions between the crust and the superfluid interior may involve the pasta layer. The observed distribution of thermal emission across neutron star surfaces, sometimes showing uneven cooling, also points to unusual conductivity properties consistent with pasta. Furthermore, the rate at which neutron stars cool after accretion outbursts matches models that include pasta scattering of neutrinos. Each of these clues supports the idea that this exotic phase exists, though final confirmation awaits future data. Beyond nuclear pasta, the matter in neutron star interiors becomes even less certain. As density increases, nucleons may give way to particles containing strange quarks, such as hyperons. Hyperons are heavier relatives of neutrons and protons, and their appearance would soften the equation of state reducing the maximum mass the star can support. However, observations of neutron stars with masses around 2 times that of the Sun suggest that hyperons may be suppressed or balanced by other effects. Another possibility is a transition to deconfined quark matter. In this scenario, neutrons and protons dissolve, and their constituent quarks flow freely in a dense liquid. Some models predict a mixed phase where regions of quark matter coexist with nuclear matter, while others allow for a pure quark core. The properties of such matter are unknown because the strong nuclear force becomes highly nonlinear under these conditions, making calculations difficult. Astrophysical observations are the only way to probe such regimes. The presence or absence of exotic cores is tested through measurements of mass and radius. If quark matter exists, it would alter the relationship between mass and radius in ways that could be detected by X-ray timing instruments, such as those on the Neutron Star Interior Composition Explorer. In addition, gravitational wave observations from mergers offer insights, because the tidal deformability of each star depends on its internal composition. Early results from the first binary neutron-star merger detected in 2017 have already placed constraints, though not yet decisive. In this way, the pasta layer connects to broader questions of dense matter physics. It represents the first departure from ordinary nuclear structures and sets the stage for possible transitions deeper within. By studying the pasta phase, scientists learn about how matter organizes when pushed beyond terrestrial conditions, and they gain a bridge to the even more exotic possibilities of hyperons or quark matter. The layered structure of a neutron star thus reflects a progression from known physics to unknown territory. At the surface lie familiar nuclei, though compressed to densities far beyond anything on Earth. In the inner crust, neutrons drip from nuclei, forming a fluid background. In the pasta layer, nuclei stretch into shapes determined by competing forces. In the core, neutrons may form a superfluid, protons may become a superconductor, and exotic particles may emerge. Each transition is marked by new physics and by new observable consequences. These insights reinforce the view that neutron stars are natural laboratories for extreme matter. They allow scientists to test theories of nuclear interaction and the strong force at conditions inaccessible to experiments on Earth. As telescopes and detectors improve the signatures of pasta, and exotic cores may become clearer, helping to resolve long-standing questions. For now, the study of nuclear pasta remains an area where theory and observation meet in cautious agreement, pointing towards structures that are strange in form yet natural in origin, hidden within the depths of every neutron star. Once the core of a massive star collapses into a neutron star, and its internal structure settles, one of the most immediately striking properties is its rotation. The conservation of angular momentum dictates that, as the star's radius shrinks by a factor of thousands, its rotation rate must increase by the same factor. This means that a core rotating once every day can be transformed into a remnant spinning several times each second. Observational data confirm this behavior, with young neutron stars often rotating at periods measured in tens or hundreds of milliseconds. The rapid spin is not only a byproduct of collapse, but a defining feature of neutron star behavior. The spin determines how energy is distributed, how magnetic fields are organized, and how radiation is emitted. The fastest rotators observed, known as millisecond pulsars, turn hundreds of times each second, but these are generally older stars that have been spun up through accretion in binary systems. In their youth, neutron stars rotate quickly on their own, then gradually lose energy and slow down. This slowing or spin down occurs because the star emits electromagnetic radiation and particle winds. The rotational energy is tapped to power these emissions. Over millions of years, a neutron star may slow to the point where it no longer produces detectable beams, though it remains present in the galaxy as a quiet remnant. The rotational stability of neutron stars is remarkable. Some pulsars serve as cosmic clocks, their pulses arriving at Earth with such regularity that they rival atomic clocks in precision. Astronomers can predict the arrival of pulses years in advance with microsecond accuracy. This makes pulsars useful tools for astrophysics, including the detection of gravitational waves through pulsar timing arrays. The extreme stability arises because the dense star resists external disturbances, and its rotation is controlled by global properties of matter at nuclear densities. Yet this stability is punctuated by sudden irregularities known as glitches. In a glitch, the star abruptly spins slightly faster than before, sometimes by a fraction of a part in 100 million. These glitches are thought to occur when the superfluid interior transfers angular momentum to the crust. The star's inner neutrons form a superfluid that rotates by creating quantized vortices. These vortices can pin to the crust and hold back some of the angular momentum. When the pinning suddenly breaks, angular momentum flows into the crust, increasing its spin. The result is observed as a glitch. Glitches provide valuable evidence of the superfluid state inside neutron stars. No other known phenomenon could produce such sudden and quantized changes. Astronomers study these events carefully to learn about the coupling between crust and core, the strength of vortex pinning, and the dynamics of superfluid matter. Another feature of rotation is precession, a slow wobble of the spin axis. Some neutron stars show signs of precession in their pulse arrival times. Precession reveals information about the star's internal structure because it depends on how mass is distributed and on the rigidity of the crust. The combination of spin-down glitches and precession paints a picture of a star that is at once highly stable and subtly dynamic. Magnetic fields play an important role in rotation as well. The strong fields of neutron stars, often billions of times stronger than Earth's field, interact with the rotation to produce electromagnetic torque. This torque carries energy away in the form of radiation and particle winds. The exact rate of spin down depends on the strength and configuration of the magnetic field. Young pulsars with strong fields slow down more quickly than old pulsars with weaker fields. This explains the wide range of observed spin periods across the population. The rotational energy released by some stars can be enormous. In the Crab pulsar, for example, rotational energy is steadily converted into the luminous nebula around it. Each second the pulsar loses rotational energy, equivalent to hundreds of thousands of times the energy output of the Sun. This energy powers the glowing filaments and synchrotron emission observed across the spectrum. The Crab pulsar demonstrates how rotation serves as a long-term energy source for surrounding space. The braking index is another observational measure of rotational behavior. It describes how the spin-down rate changes over time. For a simple dipole radiation model, the braking index should be 3. However, measured values are often less, indicating that other processes are at work. These may include particle winds, changes in magnetic field structure, or interaction with surrounding material. Each measurement of braking index adds detail to the portrait of how neutron stars evolve. Rotational alignment is also significant. The magnetic axis is often tilted relative to the spin axis. This misalignment is what allows beams of radiation to sweep through space and produce pulses when they cross Earth. Over long timescales, the axes may align, reducing the pulse's visibility. This alignment process is still being studied, but it ties directly into how long pulses remain detectable. The stability of pulsars has led to their use as tools beyond astrophysics. Pulsar timing arrays monitor dozens of millisecond pulsars to search for low-frequency gravitational waves. The idea is that passing waves stretch and compress, space-time slightly altering the arrival times of pulses. By comparing many pulsars across the sky, astronomers can detect these tiny variations. The method has already yielded evidence for a background of gravitational waves from merging supermassive black holes. This application depends on the extraordinary rotational stability of neutron stars. Even small deviations can be modelled and accounted for, making pulsars a cornerstone of precision astrophysics. The study of rotation also informs understanding of stellar birth. The initial spin rate of a neutron star carries memory of the conditions of core collapse. By observing young pulsars in supernova remnants, astronomers piece together how angular momentum is distributed during the explosion. Some stars are born spinning rapidly, while others emerge slower. The reasons for this diversity are not fully understood, and ongoing observations aim to clarify the connection between progenitor properties and neutron star rotation. Thermal and magnetic evolution couple to rotation as well. Cooling affects viscosity in the interior, which in turn influences how the star responds to stresses. Magnetic field decay alters the torque on the star and changes the spin-down rate. The interplay among these processes creates a complex but coherent picture of neutron star life. From rapid birth spin to gradual decline, from steady pulses to sudden glitches, rotation provides one of the clearest windows into the physics of dense matter. The neutron star becomes not just a remnant of collapse, but a dynamic system whose timing can be read across the cosmos. Every pulse, every irregularity, and every change in period tells a story about the forces within. One of the defining characteristics of neutron stars is their extraordinary magnetic fields, which reach intensities far beyond anything observed in other cosmic or terrestrial environments. These fields originate in part from the conservation of magnetic flux during the collapse of the progenitor star. As the stellar core shrinks from a radius of thousands of kilometers to only tens of kilometers, the magnetic field lines are compressed and intensified. If the original star possessed a field similar to that of the Sun, the resulting neutron star field can be amplified by many orders of magnitude. The rapid rotation of the new neutron star further enhances magnetic dynamo processes, producing fields that in young pulsars typically range from 100 million to 1 trillion Gauss. For comparison, Earth's magnetic field is roughly 1/2 Gauss. The structure of these magnetic fields is often approximated as a dipole like that of a bar magnet, but the reality is more complex. Higher-order multipole components may be present, and local distortions can arise from crustal stresses or differential motion in the interior. Despite these complexities, the large-scale dipole model explains much of the observed radiation and spin-down behavior of pulsars. The orientation of the magnetic axis relative to the spin axis is particularly important. When the two axes are misaligned, the beams of radiation associated with the magnetic poles sweep through space as the star rotates. This geometry produces the pulsed signals that define pulsars. Magnetic fields also govern how charged particles move near the star. The field lines guide electrons and positrons along curved paths, accelerating them to near the speed of light. As they accelerate, they emit radiation in the form of curvature, radiation, synchrotron radiation, and inverse Compton scattering. These processes generate the broad spectrum of emissions observed from radio waves to gamma rays. The magnetosphere of a neutron star, the region dominated by its magnetic field, extends far into space. Inside this magnetosphere, plasma fills the field lines sustained by pair production processes, where photons of extreme energy create electron-positron pairs. The plasma co-rotates with the star until a distance known as the light cylinder, where the co-rotation speed would equal the speed of light. Beyond this radius, field lines open outward, allowing particles to escape as a relativistic wind. This pulsar wind interacts with the surrounding interstellar medium, forming structures such as pulsar wind nebulae. The magnetic field decays over time, though the exact mechanisms remain under study. Processes such as ohmic dissipation Hall, drift and ambipolar diffusion in the crust and core redistribute and weaken the field on timescales of hundreds of thousands to millions of years. Observations show that younger neutron stars tend to have stronger fields, while older millisecond pulsars have weaker fields consistent with gradual decay. However, the rate of decay and the role of interior processes remain active research topics. Some neutron stars, known as magnetars, possess magnetic fields far stronger than typical pulsars, reaching strengths of 1 quadrillion Gauss. At these levels, the magnetic field itself alters atomic structures, compressing electron orbits and changing the physics of matter. Photons propagate differently, with vacuum polarization effects predicted by quantum electrodynamics becoming significant. In such environments, the magnetic field is not only a background influence, but an active participant in shaping observable phenomena. Magnetic fields also play a key role in the evolution of neutron star rotation. The torque generated by electromagnetic radiation and particle winds carries away angular momentum. The rate of spin down depends directly on the field strength and geometry. Stronger fields extract energy more rapidly, causing young pulsars to slow quickly, while weaker fields allow millisecond pulsars to maintain their fast rotation for billions of years. This link between magnetism and rotation defines the observable lifetime of pulsars as beacons. Evidence for the strength of neutron star magnetic fields comes from multiple observations. Cyclotron resonance features in X-ray spectra provide direct measurements of field strength in some systems. Timing measurements of spin-down rates give indirect estimates based on the dipole model. Bursts and flares in magnetars, imply magnetic stresses far beyond normal values, confirming the existence of fields of quadrillion Gauss strength. Each line of evidence supports the conclusion that neutron stars host the most intense magnetic environments known. The magnetic field also interacts with the crust storing energy that can be released suddenly. Stresses build as the field evolves and twists. When the crust yields a fracture, occurs releasing energy in the form of X-ray or gamma-ray bursts. These starquakes are most often observed in magnetars, but may also influence pulsar glitches. The link between magnetism crustal dynamics and observable emission provides a crucial tool for probing conditions deep inside the star. In the magnetosphere, the field controls the acceleration gaps where particles are lifted and accelerated. Competing models describe these gaps as existing near the polar caps, along the outer magnetosphere or near the light cylinder. Each geometry predicts different emission patterns, and observations across wavelengths are used to test these models. Recent gamma-ray observations from the Fermi Gamma-Ray Space Telescope have provided detailed maps of pulsar emission constraining the locations of these acceleration zones. The interplay of magnetic fields and rotation extends beyond the individual star. In binary systems, the field channels accreting matter, directing it to the magnetic poles where it produces X-ray hotspots. In pulsar wind nebulae, the field organizes the outflowing plasma into structures observed as toruses and jets. In mergers, the field influences the dynamics of kilonova ejecta and may contribute to short gamma-ray bursts. The presence of strong magnetic fields in neutron stars is not a secondary detail, but a central characteristic that shapes nearly every aspect of their behavior and observability. Their intensities test the limits of physics, their structures reveal the geometry of emission, and their evolution ties directly to the life history of the star. By studying these magnetic environments, scientists explore not only astrophysical phenomena, but also fundamental laws of quantum electrodynamics and plasma physics. The connection between magnetic field rotation and emission defines the pulsar phenomenon, distinguishes magnetars as a separate class, and underlies the diverse appearances of neutron stars across the sky. When neutron stars are observed as pulsars, their most distinctive feature is the regular pulse of radiation that reaches Earth. This behavior is explained by the lighthouse model, in which beams of electromagnetic radiation emerge from the magnetic poles and sweep across space as the star rotates. If Earth lies within the path of these beams, astronomers detect a pulse each time the beam crosses our line of sight. The period between pulses corresponds to the rotation period of the star, allowing precise measurements of its spin. The geometry of pulsar emission depends on the angle between the spin axis and the magnetic axis. If the two axes are nearly aligned, the beam may never cross Earth's view, and the star remains invisible as a pulsar. If the axes are significantly misaligned, the sweeping beam produces a strong and regular signal. This selection effect explains why only a fraction of neutron stars are detected as pulsars, even though many more exist unseen in the galaxy. The width of the beam and the structure of the emission pattern vary across different stars. Some pulsars emit narrow beams visible only from specific orientations, while others have wide emission cones that cover larger areas of the sky. Radio observations provide the most common means of detection, but pulsars are also observed in X-rays, gamma rays, and sometimes in optical light. Each wavelength probes different regions of the magnetosphere and different emission mechanisms. The pulse shape or profile is a crucial diagnostic tool. By averaging thousands of pulses, astronomers build stable profiles that reveal the structure of the emission beam. Changes in pulse profiles over time can indicate precession of the spin axis or evolution of the magnetic field. Some pulsars show multiple components in their profiles, suggesting complex beam geometries. The stability of these profiles is remarkable, often remaining consistent for decades, yet subtle variations carry valuable information about the star's environment. One key feature of pulsar radiation is dispersion. As radio waves travel through the interstellar medium, lower frequency waves are delayed relative to higher frequency waves because of interactions with free electrons along the path. This effect spreads the arrival time of a pulse across frequencies. By measuring dispersion, astronomers determine the column density of electrons between Earth and the pulsar, known as the dispersion measure. This not only allows correction of the pulse timing, but also provides a tool for mapping the distribution of plasma in the galaxy. The precision of pulsar timing makes it possible to detect small perturbations. Binary pulsars, where a neutron star orbits a companion, show variations in pulse arrival times due to orbital motion. Careful analysis yields orbital parameters with extraordinary accuracy. In some systems, such as the famous Hulse-Taylor binary pulsar measurements of orbital decay, provided the first indirect evidence for gravitational waves consistent with predictions of general relativity. These discoveries highlight how pulsars serve as laboratories for fundamental physics. Timing arrays extend this concept by monitoring many pulsars simultaneously. By comparing the arrival times of pulses from different parts of the sky, astronomers search for correlated deviations that would indicate the passage of low-frequency gravitational waves. This technique is sensitive to waves produced by the slow-in spiral of supermassive black hole binaries in distant galaxies. Recent results from international collaborations have reported evidence for a background of such waves, demonstrating the power of pulsar timing as a cosmic observatory. Not all pulsars emit continuously. Some exhibit nulling, where the pulses disappear for minutes, hours, or even days before resuming. Others show mode-changing switching between distinct pulse shapes. These behaviors suggest changes in the magnetosphere or particle acceleration processes, though the exact mechanisms remain uncertain. Rotating radio transients, or RRATs, emit pulses sporadically, rather than in regular sequences, revealing another mode of neutron star activity. The diversity of pulsar emission challenges models and indicates that the magnetosphere is a dynamic environment. Millisecond pulsars represent a special class. These pulsars rotate hundreds of times per second and produce extremely stable pulses. They're thought to be old neutron stars that have been spun up by accreting matter from a companion star, a process known as recycling. Because of their stability, millisecond pulsars are particularly valuable for timing arrays and precision astrophysics. Their rapid spin also places them at the edge of stability, testing the limits of neutron star structure. The discovery of pulsars themselves was a landmark in astronomy. In 1967, Jocelyn Bell Burnell and Anthony Hewish detected regular radio pulses from a source later identified as a rapidly rotating neutron star. The finding confirmed theoretical predictions of neutron stars and opened a new field of study. Since then, thousands of pulsars have been catalogued, and each new discovery adds to the understanding of stellar evolution and dense matter physics. Multi-wavelength observations continue to refine the lighthouse model. Gamma-ray pulsars observed by the Fermi Gamma Ray Space Telescope show emission at high altitudes in the magnetosphere, while radio observations trace regions closer to the surface. X-ray pulsars reveal hotspots where accreted matter strikes the surface, or where magnetic fields channel energy. Together, these data build a comprehensive picture of how beams are generated and sustained. The precision of pulsar timing also allows the detection of exoplanets. Tiny variations in pulse arrival times indicate the gravitational influence of orbiting bodies. The first confirmed exoplanets were discovered around a millisecond pulsar, demonstrating the extraordinary sensitivity of this method. Although such systems are rare, they reveal that planets can form or survive even in the extreme environment around neutron stars. The role of pulsars as cosmic lighthouses extends beyond their own nature. They serve as distance markers for probing the galaxy, as timing tools for gravitational wave detection, as laboratories for plasma physics, and as test beds for general relativity. Their beams of radiation sweeping steadily across space transform compact remnants of stellar death into instruments of cosmic measurement. The consistency of pulses combined with the diversity of behaviors such as nulling glitches and mode changes demonstrates both the stability and complexity of these remarkable stars. As observational capabilities grow, the details of emission geometry, beam composition and magnetospheric dynamics continue to sharpen. Each new measurement not only refines the lighthouse model, but also deepens the understanding of how fundamental forces operate in one of the universe's most extreme environments. The remarkable regularity of pulsar signals makes any deviation from the expected pattern especially noticeable. Among the most studied of these deviations are glitches, sudden increases in rotation rate that interrupt the smooth spin down of a neutron star. The magnitude of a glitch is often very small, perhaps a fractional change of 1 part in 100 million. Yet such events are significant because they reveal processes deep inside the star. The prevailing explanation involves the interaction between the crust and the superfluid interior. In the outer layers of the star, the rigid crust rotates at a steady pace, gradually slowing as energy is lost. Inside, however, the neutrons form a superfluid that does not spin down smoothly. Instead, the superfluid rotates through the formation of quantized vortices. These vortices can pin themselves to the lattice of the crust, temporarily locking the superfluid rotation to the crust. Over time, as the crust continues to slow, tension builds between the two components. When the pinning suddenly fails, vortices unpin and move outward, transferring angular momentum from the superfluid to the crust. The crust spins up abruptly and observers detect a glitch. Evidence for this model comes not only from the occurrence of glitches but from the way stars behave afterward. Many glitches are followed by a relaxation period during which the spin gradually returns to its pre-glitch trend. This relaxation is interpreted as the re-establishment of coupling between the crust and the superfluid. By studying the size and frequency of glitches, astronomers learn about the strength of vortex pinning the distribution of superfluid regions and the elasticity of the crust. Not all neutron stars glitch in the same way. Some show frequent small glitches while others display rare but large ones. The Vela pulsar is known for producing glitches approximately every few years, providing a valuable dataset for study. The Crab pulsar also glitches but with smaller amplitudes. The diversity of glitch behavior suggests that internal conditions vary from star to star depending on age, magnetic field strength, and thermal state. Alongside glitches, pulsars exhibit timing noise, a more gradual and irregular wandering of pulse arrival times. This noise is thought to arise from small variations in rotation rate caused by processes in the magnetosphere or interior. Although less dramatic than glitches, timing noise complicates the use of pulsars as precise cosmic clocks. Understanding its origins remains an important area of research. Some pulsars also show sudden changes in their emission properties associated with timing irregularities. Mode switching, for example, involves transitions between different pulse profile shapes that coincide with changes in spin-down rate. These links suggest that magnetospheric conditions can alter both emission and rotational dynamics. By monitoring these changes, scientists explore the connection between internal physics and external radiation. Another class of irregularity involves spin-ups in accreting pulsars. In binary systems where matter flows onto a neutron star, angular momentum from the accreted material can cause the star to rotate faster. This accretion-driven spin-up differs from glitches, but also reflects the transfer of angular momentum. Some accreting pulsars transition between spin-up and spin-down, depending on accretion rate, providing insight into the balance of forces in binary evolution. Precision timing of pulsars extends into applications beyond astrophysics. For example, when pulsars glitch, the precise measurement of the event allows tests of theories about superfluidity and superconductivity at nuclear densities. These are conditions that cannot be replicated in laboratories on Earth. The star itself becomes an experimental platform with timing data serving as the readout. The physics of superfluids in neutron stars resembles phenomena studied in liquid helium, but at vastly higher densities and energies. Vortex pinning, vortex creep, and collective unpinning events are subjects of active research uniting astrophysics with condensed matter physics. Observations of glitches also impose constraints on neutron star mass and radius. The size of the angular momentum reservoir available in the superfluid depends on the distribution of matter inside the star. If the inner crust alone participates, only a limited fraction of angular momentum can be stored. Some large glitches suggest that superfluid regions in the core may also contribute. This inference influences models of the equation of state, which in turn governs the maximum mass and stability of neutron stars. The study of glitches is therefore tied directly to fundamental questions about dense matter. Timing irregularities are detected with radio telescopes that monitor pulsars for years or decades. Each pulse is recorded, and the cumulative data reveal trends invisible in single observations. The patience of long-term monitoring pays off when a glitch occurs, sometimes only a few times in a century for certain pulsars. International collaborations maintain these timing campaigns, ensuring continuity across generations of astronomers. Glitches are also important for understanding magnetars. These highly magnetized neutron stars show both radiative bursts and rotational glitches. In some cases, a glitch coincides with an X-ray outburst, linking interior processes with magnetic field stresses. This connection strengthens the view that magnetism, crustal dynamics, and superfluid motion are intertwined. Another dimension of study is the recovery behavior after glitches. Some stars show partial relaxation, returning only partway to the original spin-down trend. Others show over-recovery where the spin-down rate becomes faster than before. These variations challenge simple models and indicate complex coupling between multiple internal components. Each recovery curve provides a fingerprint of the internal dynamics. Timing irregularities have even been proposed as probes for gravitational waves. Although pulsar timing arrays focus on long-term stability, glitches create sudden changes that could, in principle, be correlated with other astrophysical events. While this remains speculative, it illustrates the many ways pulsar timing intersects with frontier research. The cumulative picture from glitches, timing noise, and irregularities is that neutron stars, while stable in many respects, harbor dynamic processes within. Beneath the calm regularity of pulses lies a core of superfluid vortices, crustal stresses, and magnetic fields in constant adjustment. Each irregularity that reaches our telescopes is a window into these hidden dynamics. Observers continue to refine models, but the essential message is clear. The extreme environment of neutron stars produces behaviors that combine stability with sudden disruption, regularity with surprise. In this balance, scientists find one of the most compelling laboratories for the study of matter under extreme conditions. Among the various categories of neutron stars, magnetars stand out because of their uniquely powerful magnetic fields and the dramatic phenomena that arise from them. whereas ordinary pulsars typically have magnetic fields of 1,000,000,000,000 Gauss, or less magnetars reach intensities up to 1,000,000,000,000 Gauss. At such levels, the magnetic field dominates not only the behavior of charged particles around the star, but also the structure of the crust and the propagation of light itself. The energy stored in a magnetar's field exceeds its rotational energy, making magnetism the primary driver of observable activity. The existence of magnetars was first proposed to explain soft gamma repeaters sources that emit short and intense bursts of gamma rays. Later, anomalous X-ray pulsars were also identified as magnetars, because their persistent high-energy emission could not be explained by rotation alone. Today, these two categories are understood as different observational manifestations of the same type of object. Their bursts, flares, and persistent emissions are all consistent with the presence of magnetic fields of extreme strength. Inside a magnetar magnetic field, lines are twisted and stressed as they evolve. These stresses build pressure on the solid crust, gradually deforming it until the crust can no longer withstand the force. When the crust fractures, the sudden movement rearranges the magnetic field and releases stored energy in the form of X-rays and gamma rays. These events are called starquakes. Starquakes produce bursts that can last from fractions of a second to several seconds. In some cases, they are followed by extended tails of emission as the magnetosphere reconfigures. The energy released in a typical burst may be equivalent to what the Sun emits in years, all delivered in moments. The detection of such bursts from across the galaxy underscores the extraordinary power of magnetic stresses. The most dramatic events associated with magnetars are giant flares. Only a handful have been observed, but their intensity is striking. The giant flare of 1979 from SGR 052666 released energy in a fraction of a second that briefly saturated detectors and was observable even after scattering through Earth's atmosphere. Later flares in 1998 and 2004 confirmed the existence of this class of events. These flares release energies of around 100,000 trillion joules, producing gamma rays intense enough to affect Earth's ionosphere even from tens of thousands of light-years away. Such flares demonstrate that magnetars are among the most energetic astrophysical objects short of black hole mergers. Magnetar activity is not limited to bursts and flares. Their persistent X-ray luminosity is higher than can be powered by rotation alone. This persistent emission is thought to arise from the gradual decay of the magnetic field, which heats the crust and surface. Over thousands of years, this process sustains thermal radiation, detectable by X-ray telescopes. Observations confirm that magnetars tend to be relatively young neutron stars, consistent with the idea that their fields decay on timescales of 10,000 to 100,000 years. Another feature of magnetars is their slow rotation. Whereas young pulsars often rotate many times per second, magnetars usually have periods of a few seconds. This reflects their rapid spin down under the influence of intense magnetic braking. The strong fields extract rotational energy efficiently, leaving magnetars as slowly rotating yet highly luminous sources. This distinction helps classify them observationally. Theoretical models predict additional effects of such strong magnetic fields. Quantum electrodynamics describes how vacuum polarization alters photon propagation, leading to phenomena such as birefringence, where light polarized in different directions travels at slightly different speeds. Although challenging to detect, these effects may be observable with sensitive X-ray polarimetry. If confirmed, they would provide direct evidence for quantum processes in ultra-strong fields. Magnetars also show connections to other transient phenomena. Some fast radio bursts, millisecond flashes of radio waves of extragalactic origin, have been linked to magnetar activity. In 2020, a fast radio burst was observed from the galactic magnetar SGR 1935+2-2154, providing strong evidence that at least some fast radio bursts arise from magnetar flares. This link strengthens the importance of magnetars not only as exotic stellar remnants, but as contributors to broader astrophysical mysteries. Starquakes and magnetic stresses also have implications for gravitational wave emission. A sudden rearrangement of the crust or field could generate vibrations that emit weak gravitational signals. While current detectors are not sensitive enough to confirm such emissions, future observatories may test these predictions. If detected, they would open a new window into magnetar dynamics. The crust of a magnetar must bear extraordinary stresses. Models suggest that its strength is exceeded during starquakes, producing fractures that extend over large areas. These fractures not only release energy, but also shift the configuration of the magnetic field outside the star. The twisted field lines accelerate particles and produce bursts of radiation. In the aftermath, the magnetosphere settles into a new state until stresses build again. This cycle explains the recurring bursts observed in soft gamma repeaters. Magnetars also interact with their surroundings. Their strong winds and flares inject energy into the surrounding interstellar medium, creating nebulae that glow in X-rays. In some cases, extended emission following a flare illuminates nearby material, providing indirect information about the environment. These interactions show that magnetars influence not only their own surfaces, but also their galactic neighborhoods. Observations of magnetars rely on space-based telescopes, sensitive to X-rays and gamma rays. Instruments such as Swift Fermi, XMM, Newton and Chandra have recorded bursts, spectra and persistent emission. The data reveal a range of behaviors from frequent short bursts to rare giant flares. Each observation constrains models of magnetic stress field decay and crustal dynamics. Despite progress, many questions remain. The exact mechanism that initiates a starquake, the detailed structure of magnetar fields, and the full connection to fast radio bursts are still under study. The rarity of giant flares means that each detection is crucial, but decades may pass between events. Continued monitoring of known magnetars and the discovery of new ones remain priorities for astrophysics. In summary form, magnetars are neutron stars where magnetic energy exceeds all other energy reservoirs, dictating their evolution and emissions. Their starquakes, bursts, and giant flares illustrate the extremes of magnetic stress and provide insight into physics inaccessible in laboratories. As space telescopes expand observational coverage and as theoretical models improve, magnetars remain at the frontier of high-energy astrophysics, linking the study of dense matter with questions of magnetism, radiation, and cosmic transients. The most dramatic expressions of magnetar activity are the rare and powerful events known as giant flares. These flares differ from the more common short bursts because they release an extraordinary amount of energy in a very brief interval, often within a fraction of a second. The initial spike is followed by a pulsating tail lasting several minutes, modulated at the rotation period of the star. Such events are thought to arise when magnetic stresses in the crust and magnetosphere reach a critical point, producing a catastrophic rearrangement of the magnetic field and releasing energy that had been stored for centuries. Only 3 confirmed giant flares have been observed so far. The first, recorded in 1979 from SGR 05666 in the Large Magellanic Cloud, was so intense that it overwhelmed detectors and was noticed even by instruments not designed for gamma rays. The second, from SGR 1900+14 in 1998, produced a brilliant flash visible across the galaxy. The third, from SGR 1806-20 in 2004, remains the most powerful, releasing in a fraction of a second more energy than the Sun emits in hundreds of thousands of years. The afterglow from this event was detectable for months, and the gamma rays briefly disturbed Earth's ionosphere, demonstrating the reach of magnetar phenomena across interstellar distances. The mechanism behind giant flares involves the buildup of stress in the magnetic field in the crust. As the internal magnetic field evolves, it can twist and distort the external magnetosphere. When the tension becomes too great, the crust yields fracturing in a large-scale starquake. This sudden motion alters the configuration of the external field, releasing energy in the form of an electromagnetic explosion. The initial spike corresponds to the rapid release, while the tail represents trapped plasma oscillating in the closed magnetic field lines and radiating as it cools. Observationally, the pulsating tail provides a direct measurement of the star's rotation period, confirming the link between magnetars and these flares. The rarity of giant flares makes each one invaluable for research. Because they are so energetic, they can be detected across vast distances, raising the possibility that similar events in other galaxies may appear as short gamma-ray bursts. Indeed, some fraction of the short gamma-ray bursts detected outside the Milky Way may be extragalactic magnetar giant flares. Distinguishing between merger-driven bursts and magnetar flares remains an ongoing challenge requiring careful analysis of spectra durations and afterglows. The potential overlap highlights the importance of magnetars not only in neutron star astrophysics but in high-energy astronomy more broadly. Giant flares also influence the surrounding environment. The intense radiation and particle outflows can sweep through nearby interstellar gas heating and ionizing it. In some cases, echoes of the flare are observed as the radiation reflects off dust clouds, allowing astronomers to map the environment and measure distances. These light echoes provide rare three-dimensional perspectives on the vicinity of magnetars. The physical conditions during a giant flare push the limits of known physics. The magnetic field strength can exceed the so-called quantum critical field, where the energy of an electron's motion in the field matches its rest mass energy. In this regime, quantum electrodynamics predicts novel effects such as vacuum birefringence and photon splitting. Detecting signatures of these processes during giant flares would provide experimental tests of fundamental theory under conditions unattainable on Earth. The 2004 flare from SGR 1806-20 provided some of the best data, with multiple satellites recording the event across energy bands. Analysis of this data continues to yield insights into plasma dynamics, spectral features, and temporal evolution. Yet even with such a wealth of information, questions remain about what triggers the final catastrophic release, how the crust fractures propagate, and how the magnetosphere responds. Future flares will be crucial to refining models. The energy budget of giant flares is also of interest. The rotational energy of a magnetar is insufficient to power such events, pointing clearly to magnetic energy as the source. Estimates suggest that the internal magnetic field may be even stronger than the external field inferred from spin-down rates. This hidden energy reservoir supplies the fuel for flares, gradually building over thousands of years until released in seconds. The long quiet intervals between flares fit this picture as the star slowly accumulates magnetic stress before yielding. The potential for gravitational wave emission during giant flares has been explored as well. A starquake or rapid reconfiguration of mass distribution could generate waves detectable by sensitive instruments. So far, searches during known flares have not yielded signals, but upper limits help constrain models. As detectors improve, the possibility of catching a gravitational wave counterpart to a magnetar flare remains open. The connection between magnetar flares and fast radio bursts has become a major focus in recent years. The detection of a fast radio burst from SGR 1935+2 Pulsar in 2020, coincident with an X-ray burst, demonstrated that magnetars can indeed produce millisecond radio flashes. While not all fast radio bursts may originate from magnetars, this observation provides a concrete link suggesting that some extragalactic fast radio bursts could be the distant signatures of magnetar activity. This reinforces the idea that giant flares and related processes are not isolated curiosities, but integral to the broader astrophysical landscape. The study of giant flares requires global coordination. Because they occur unpredictably wide, field monitors are essential. Networks of satellites, including Swift Fermi and Integral, provide continuous coverage of the sky. Ground-based observatories follow up in radio-optical and X-ray bands. Together, these efforts maximize the scientific return from rare events. Each detection informs not only the physics of magnetars, but also the behavior of matter and fields under extreme conditions. Despite their violence, giant flares do not destroy the magnetar. After each event, the star remains intact, though its rotation may shift slightly, and its persistent emission may change. The recurrence of bursts and the long-term activity of known magnetars indicate that these stars can undergo multiple flares over their lifetimes. The cycle of stress build-up, release and recovery defines their observable evolution. As astronomers await the next giant flare, theoretical work continues to explore how magnetic energy is stored, how crustal fractures propagate, and how plasma dynamics shape the emission. When the next event occurs, the combined capabilities of modern observatories may capture details never seen before, from polarization patterns to gravitational wave signatures. Such data would bring us closer to understanding the full scope of magnetar power and the role of giant flares in the universe. Neutron stars in binary systems reveal another side of their nature, one dominated by the flow of matter from a companion star. When a neutron star orbits close enough to another star, gas can be drawn from the companion by the strong gravity of the neutron star. This process is known as accretion, and it is one of the most efficient energy conversion mechanisms in the universe. As the gas falls inward, gravitational potential energy is converted into heat and radiation, producing intense X-ray emission that marks these systems as X-ray binaries. The gas typically spirals in through an accretion disk, a flat rotating structure formed by the conservation of angular momentum. As material moves inward through the disk, it heats to millions of degrees, radiating strongly in X-rays. The inner regions of the disk reach extreme conditions, and the flow of matter becomes tightly coupled to the magnetic field of the neutron star. Depending on the field strength, accreted gas may be channeled along magnetic field lines onto the magnetic poles, creating hotspots on the surface. As the star rotates, these hotspots produce pulsations in X-rays, leading to the class of objects called accretion-powered pulsars. The luminosity of X-ray binaries can rival or exceed that of an entire galaxy of stars when viewed in X-rays. Because accretion converts a significant fraction of the infalling matter's rest mass into energy, these systems shine with efficiency unmatched by nuclear fusion. Observations show that X-ray binaries vary in brightness over time, sometimes dramatically. These variations reflect changes in accretion rate instabilities in the disk or interactions with stellar winds from the companion. Some systems undergo regular outbursts as mass transfer increases temporarily, while others maintain steady accretion. One of the most remarkable phenomena associated with accretion is the occurrence of thermonuclear bursts on the surface of the neutron star. As matter accumulates on the surface, hydrogen and helium build up under increasing pressure. When conditions become extreme enough, nuclear fusion ignites, suddenly releasing energy in a runaway reaction. The result is a burst of X-rays that rises rapidly and then decays over tens of seconds. These bursts, known as Type Y X-ray bursts, provide direct evidence of nuclear processes occurring on the neutron star surface. They allow scientists to study nuclear reactions in conditions of density and gravity inaccessible to terrestrial experiments. Repeated bursts from the same source reveal cycles of accumulation and ignition, turning the neutron star into a cosmic laboratory for thermonuclear physics. In some cases, especially when accretion is rapid, bursts may involve not only hydrogen and helium, but also heavier elements created during earlier burning. This leads to complex burst behaviors, including superbursts that last hours and involve carbon ignition deep below the surface. Observations of such events constrain models of heat transport, nuclear reaction rates, and crustal properties. By analyzing burst spectra, astronomers can measure surface temperatures, radii, and compositions, offering rare glimpses of the neutron star's outer layers. Accretion also drives spin evolution. As matter spirals onto the neutron star, it transfers angular momentum, causing the star to rotate faster. This process explains the origin of millisecond pulsars, which are thought to be old neutron stars spun up through long periods of accretion. These recycle pulsars maintain rapid rotation long after accretion ceases serving as highly stable clocks. Evidence for this spin-up comes from observations of accreting millisecond X-ray pulsars, where spin periods of a few milliseconds are measured directly. The process of recycling illustrates how binary interactions shape the life history of neutron stars. The interplay between accretion and magnetic fields is complex. If the magnetic field is strong, it can truncate the accretion disk at some distance from the star. Matter then flows along magnetic funnels onto the poles, creating X-ray pulsations. If the field is weak, the disk can extend almost to the surface, and accretion becomes more uniform. In some regimes, the magnetic field can even expel matter, halting accretion in what is called the propeller effect. Observationally, these regimes produce different signatures, from steady X-ray pulsations to erratic variability. X-ray binaries are classified into high-mass and low-mass systems depending on the mass of the companion. High-mass X-ray binaries involve massive stars that lose matter through strong winds, while low-mass systems involve smaller stars transferring matter through Roche lobe overflow. Each type offers different insights. High-mass systems trace young stellar populations, while low-mass systems can persist for billions of years, allowing the long-term study of accretion and evolution. Accretion processes also influence the emission of gravitational waves. In rapidly rotating, accreting neutron stars, asymmetries in the crust, caused by uneven heating or magnetic stresses, could create small deformations. These deformations would emit continuous gravitational waves as the star spins. Searches for such signals are ongoing, with detectors like LIGO and Virgo, though none have yet been confirmed. If detected, they would provide direct probes of the neutron star's interior and crustal structure. Observations of X-ray binaries across the electromagnetic spectrum enrich the understanding of these systems. Optical observations reveal the companion star and the dynamics of mass transfer. Radio observations detect jets launched from some systems, showing that accretion can power collimated outflows. These jets, moving at relativistic speeds, carry energy and matter far into space, linking neutron star accretion to the broader phenomenon of astrophysical jets seen in black hole systems and active galaxies. X-ray binaries are also stepping stones to more violent events. When two neutron stars orbit each other, accretion processes can occur until gravitational wave emission brings them together in a merger. Such systems are rare but crucial as they produce colonovae and contribute to the cosmic production of heavy elements. In this way, accretion connects the daily observable phenomena of bursts and pulses to the grander events of stellar mergers. Thermonuclear bursts from accreting neutron stars also provide constraints on the equation of state of dense matter. The radiation from bursts can reach the Eddington limit where outward radiation pressure balances gravity. Measuring this limit gives an estimate of the mass and radius of the star. Such measurements, though challenging, contribute to narrowing down models of dense matter. Repeated observations over years build statistical samples that refine these constraints. The study of accreting neutron stars is therefore multifaceted. It encompasses the physics of disks, magnetic fields, nuclear burning jets, and gravitational waves. Each observation provides a piece of the puzzle, and together they reveal how neutron stars interact with their companions and environments. These systems are not rare curiosities but significant contributors to the X-ray sky, dominating surveys and shaping understanding of stellar remnants. Through accretion and bursts, neutron stars display behaviors that extend knowledge of physics from the nuclear to the galactic scale. When a neutron star emits a steady flow of relativistic particles, the outflow interacts with the surrounding interstellar medium to form a pulsar wind nebula. This structure is created as the rotational energy of the star is converted into winds of electrons and positrons that stream outward at nearly the speed of light. The wind carries both particles and magnetic fields, and when it collides with slower moving material from the progenitor supernova, a shock forms. At this shock, particles are accelerated to extremely high energies, producing synchrotron radiation that glows across the spectrum from radio waves to X-rays and gamma rays. The Crab Nebula is the most famous example of such a pulsar wind nebula. At its center lies the Crab Pulsar, which injects energy into the nebula through its particle wind. The nebula glows brightly in optical light, but more importantly it shines in X-rays and gamma rays because of synchrotron processes. High-resolution images from telescopes such as Chandra reveal intricate structures, rings, jets, and filaments shaped by the pulsar's wind and magnetic field. These features change over time, showing that the nebula is dynamic, with energy being deposited continuously by the central pulsar. The shape and brightness of a pulsar wind nebula depend on the spin-down energy of the pulsar and the density of the surrounding medium. Young energetic pulsars with high spin-down rates create bright and compact nebulae, while older or less powerful pulsars produce fainter structures. The interaction between the pulsar wind and the expanding supernova remnant also evolves. Early on, the nebula is confined by dense supernova ejecta, but as the remnant expands and thins, the pulsar wind can push farther, altering the nebula morphology. Eventually, when the pulsar escapes its original remnant due to its high velocity, it can create a bow-shock nebula as it plows through interstellar gas. Bow-shock nebulae display comet-like shapes with the pulsar at the head driving a shock front. These structures observed in radio and X-ray images show how pulsar winds shape the interstellar environment on scales of light years. The study of pulsar wind nebulae provides information about both the central pulsar and the surrounding space. The spectrum of synchrotron radiation reveals the energy distribution of particles, which in turn reflects acceleration mechanisms at the shock. Observing variability in brightness and structure shows how energy is injected and redistributed. Polarization measurements give clues about magnetic field orientation, while overall luminosity traces the energy budget of the pulsar. Some pulsar wind nebulae also produce inverse Compton emission, where high-energy electrons scatter background photons up to gamma-ray energies. This adds another component to the spectrum and allows constraints on the density of seed photons such as cosmic microwave background or starlight. These gamma-ray detections connect pulsar wind nebulae to broader studies of high-energy astrophysics. Supernova remnants often coexist with pulsar wind nebulae, providing a layered view of stellar death. The outer shell of the remnant, composed of shock-heated gas from the original explosion, expands outward, while the inner nebula glows with energy from the pulsar. Together they form composite remnants where observations across multiple wavelengths reveal both thermal emission from hot gas and non-thermal emission from relativistic particles. The interplay between these regions shows how energy from a collapsed core continues to shape the surrounding interstellar medium for thousands of years. The Crab Nebula has also served as a standard candle in X-ray astronomy, because its brightness was thought to be constant. However, recent observations revealed unexpected variability in gamma rays, challenging assumptions and showing that even well-studied systems can surprise. This variability indicates that particle acceleration in the nebula can reach extreme energies on short timescales, rivaling processes near black holes. The existence of jets in some pulsar wind nebulae demonstrates the role of magnetic fields in collimating outflows. These jets extend outward along the spin axis of the pulsar while equatorial rings form perpendicular to it. The geometry suggests that the pulsar wind is anisotropic, stronger in the equatorial plane, and focused along the poles. The changing brightness of these features on timescales of months shows that the nebula is not static but continually reshaped by the pulsar's activity. Pulsar wind nebulae also contribute to the population of cosmic rays in the galaxy. The high-energy particles accelerated at shocks may escape into interstellar space, joining the diffuse cosmic ray background. Understanding this contribution requires modelling the diffusion of particles through the nebula and into the surrounding medium. Measurements of positron excesses in cosmic rays at Earth have prompted studies of pulsars and their nebulae as potential sources. Observations of TV gamma rays from some nebulae support this idea, confirming that pulsar winds accelerate particles to extreme energies. Another aspect of study is the motion of pulsars through space. Many neutron stars receive a natal kick at birth, propelling them at hundreds of kilometers per second. When such a pulsar moves through interstellar gas, it can create a bow shock nebula, where the wind is confined by ram pressure. These structures, seen in X-rays and H-alpha emission, trace the path of runaway pulsars and reveal properties of the interstellar medium they encounter. The length and shape of the bow shock provide information about wind power and ambient density. Multi-wavelength studies of pulsar wind nebulae and supernova remnants are essential. Radio observations map synchrotron emission at lower energies. X-rays reveal the hottest and most energetic regions, and gamma rays probe inverse Compton processes. Each band adds to the full picture of how pulsar winds deposit energy. Simulations of magneto-hydrodynamic flows help interpret these data-reproducing structures like Tory jets and filaments. Pulsar wind nebulae thus stand as visible markers of the invisible processes of particle acceleration and magnetic field interaction. They transform the rotational energy of neutron stars into glowing clouds that persist for thousands of years, illuminating the physics of shocks, plasmas, and cosmic rays. By studying them, scientists connect the compact interiors of neutron stars to the diffuse interstellar environment, showing how the death of a star continues to shape the galaxy long after the supernova fades. When two neutron stars orbit one another in a close binary, their mutual gravity binds them in a slow spiral that can last hundreds of millions of years. Over time, the system loses orbital energy through the emission of gravitational waves. These waves are ripples in space-time predicted by general relativity carrying energy outward at the speed of light. As the orbit decays, the two stars draw closer, their orbital period shrinking, and eventually the stars merge. This process has profound consequences for astrophysics, both as a source of detectable gravitational waves and as a site where heavy elements are created. The first direct detection of a binary neutron star merger occurred in 2017 when the LIGO and Virgo observatories measured gravitational waves from the event now called GW170D17. The signal lasted over a minute, showing the inspiral as the stars orbited hundreds of times per second before coalescing. The detection confirmed that neutron star mergers are real and observable, opening a new era of multi-messenger astronomy. Within seconds of the merger signal, space-based observatories detected a short burst of gamma rays, establishing a link between binary neutron star mergers and short gamma ray bursts. Over the following days, telescopes observed a kilonova, an optical and infrared transient powered by the radioactive decay of heavy elements synthesized in the ejecta. The kilonova faded over weeks, but its spectral features confirm the production of R-process elements such as gold and platinum. This event provided direct evidence that neutron star mergers are key sites of heavy element formation in the universe. The dynamics of a merger involve multiple stages. During the inspiral tidal forces deform the stars, imprinting information about their internal structure onto the gravitational wave signal. This tidal deformability depends on the equation of state of dense matter, so precise measurements allow constraints on neutron star radii and stiffness. At the moment of collision, matter is ejected at high velocities, forming outflows that become the kilonova. Depending on total mass, the remnant may collapse promptly into a black hole, or survive temporarily as a hypermassive neutron star before collapsing. In either case, the merger releases enormous amounts of energy across multiple channels. Gravitational wave detectors record the inspiral, but the final moments of merger and collapse emit higher frequency waves that current instruments cannot fully resolve. Future detectors with improved sensitivity may capture these phases, revealing more about the transition to black holes and the behavior of matter at extreme densities. Electromagnetic observations complement gravitational waves. The gamma-ray burst observed with GW170D17 was weaker than typical short bursts, likely because it was viewed off-axis. This demonstrated that relativistic jets from mergers can be structured with energy concentrated along narrow cores. Follow-up radio observations showed afterglows consistent with the jet interacting with interstellar gas. These data linked short gamma-ray bursts conclusively to neutron star mergers, solving a long-standing question. The kilonova observed after GW70117 matched theoretical predictions developed over decades. As neutron-rich matter is ejected and undergoes rapid neutron capture, unstable nuclei are formed that decay radioactively. The decay releases heat, powering the glow. The color of the kilonova changes from blue to red as heavier elements form and opacity increases. By modeling light curves and spectra, astronomers estimate the amount of material ejected and the types of elements produced. This confirms that mergers contribute significantly to the cosmic inventory of heavy elements. The significance of multi-messenger astronomy lies in the combination of signals. Gravitational waves provide direct measurements of masses and orbital dynamics. Gamma rays reveal jet formation. Optical and infrared light from kilonovae trace nucleosynthesis. Radio afterglows map jet interactions. Together, these observations give a holistic picture of the event, each channel reinforcing and expanding the others. This synergy was realized fully in 2017 and has since guided preparations for future detections. The rate of binary neutron star mergers in the universe is now constrained by gravitational wave surveys. Although only a few events have been detected so far, the data suggest that such mergers occur frequently enough to account for much of the R-process enrichment of galaxies. This connection ties compact object physics directly to galactic chemical evolution, and even to the origin of elements on Earth. Future detections will refine these rates and clarify the diversity of merger outcomes. The merger process also has implications for the maximum mass of neutron stars. If the combined mass exceeds a critical threshold, collapse to a black hole occurs promptly. If not, a hypermassive neutron star may persist for milliseconds or longer, supported temporarily by differential rotation and thermal pressure. The lifetime of this remnant affects the amount of ejecta and the strength of electromagnetic counterparts. Observationally, hints of extended emission in X-rays and radio may indicate long-lived remnants in some cases. Another avenue of study involves neutrinos. During merger, vast numbers of neutrinos are emitted, carrying away energy and altering the composition of ejecta by changing neutron to proton ratios. Although no neutrinos have yet been detected from neutron star mergers, future detectors may capture them, adding a further messenger to the suite. Such detections would provide direct insight into the weak interactions that govern nucleosynthesis. Binary neutron star mergers also serve as laboratories for fundamental physics. The speed of gravitational waves was confirmed to equal the speed of light within tight limits by comparing arrival times of waves and gamma rays. This result constrained alternative theories of gravity and reinforced general relativity. Constraints on the equation of state jet formation and heavy element production all emerge from the same events, illustrating the power of these natural experiments. Observatories worldwide now coordinate to follow up gravitational wave alerts. Networks of telescopes scan the sky to find electromagnetic counterparts within hours of a detection. The localization of GW170A817 to a specific galaxy, NGC 4993, demonstrated the effectiveness of this coordination. With upgrades to detectors, more events will be found at greater distances, challenging astronomers to detect fainter counterparts, but promising a rich harvest of data. The future of neutron star merger studies lies in improved sensitivity and broader coverage. Next-generation gravitational wave observatories, such as the Einstein Telescope and Cosmic Explorer, will probe deeper into the universe, detecting thousands of mergers per year. New space telescopes with infrared capability will capture kilonova light curves in detail. Together, these instruments will transform the study of compact binaries into a precision science. The merger of neutron stars thus stands as one of the most powerful and revealing processes in astrophysics. It links stellar evolution, nuclear physics, relativity, and cosmology in a single phenomenon. Each detection provides not just one discovery, but a chain of interconnected insights, from the behavior of dense matter to the origin of elements to the testing of fundamental physics. The quiet spiral over millions of years ends in a moment of extraordinary release, visible across the cosmos through multiple messengers. Among the most puzzling and energetic signals discovered in modern astrophysics are fast radio bursts, sudden flashes of radio waves lasting only a few milliseconds, yet releasing as much energy as the Sun does in days. First identified in 2007 from archival data, these bursts were initially mysterious because they appeared bright, short, and widely dispersed, implying extragalactic origins. Since then, hundreds have been detected, and the challenge has been to identify their sources. Evidence now strongly suggests that at least some fast radio bursts are produced by magnetars, though the full range of progenitors may be diverse. The key observational property of fast radio bursts is their dispersion measure. The pulses arrive at different times depending on frequency, with lower frequencies delayed more strongly as they pass through ionized gas. The large dispersion measures observed indicate that many bursts come from far beyond the Milky Way, often billions of light-years away. This cosmological distance, combined with their brightness, implies extraordinary luminosities. Such immense energies require compact and powerful engines pointing naturally to neutron stars. In 2020, a breakthrough occurred when the galactic magnetar SGR 1935+2 produced a millisecond radio burst coincident with an X-ray flare. The radio burst was less luminous than extragalactic fast radio bursts, but still orders of magnitude stronger than any normal pulsar emission. This event established that magnetars are capable of producing fast radio burst-like signals. While it does not prove that all fast radio bursts come from magnetars, it confirms that at least some do, providing a direct link between two areas of research. The mechanisms proposed for fast radio burst emission generally involve sudden reconfigurations of magnetic fields, starquakes or magnetospheric shocks. In magnetar, stresses in the crust or field can trigger reconnection events that accelerate particles and produce coherent radio emission. Alternatively, interactions between magnetar winds and surrounding plasma may create shocks that radiate bursts. Each model must account for the short duration, high brightness and broad frequency range of the bursts. The fact that some fast radio bursts repeat adds complexity. Certain sources emit multiple bursts over months or years, sometimes with clustering in time. Repeating behavior suggests that the underlying engine survives each burst consistent with magnetar activity, rather than catastrophic events like mergers. Other sources appear to burst only once, or at least so rarely that repeats have not been detected. This diversity hints at multiple channels of production, or at differences in magnetar environments. Observations have revealed additional patterns. Some repeating bursts show periodic activity windows turning on and off over cycles of weeks or months. This could be due to precession binary interactions or modulation by stellar winds. Polarization measurements show that many fast radio bursts are highly polarized, indicating strong magnetic fields in their environments. Rotation measures, which track the twisting of polarization as radio waves travel through magnetized plasma, are often large, consistent with dense and turbulent regions around young magnetars. Local environments appear to play a major role. Many bursts are associated with host galaxies that have active star formation, suggesting that young magnetars born from recent supernova or stellar explosions are likely sources. In some cases, precise localization has tied bursts to regions of intense activity, or to compact persistent radio sources, possibly nebulae powered by magnetar winds. These associations reinforce the magnetar connection, while also indicating that the broader galactic context shapes the bursts. The extreme brightness of fast radio bursts allows them to be used as probes of the cosmos. As the signals travel across intergalactic space, they encounter free electrons in the cosmic web. By measuring dispersion measures from many bursts at known distances, astronomers can estimate the total density of baryons in the universe, addressing the long-standing problem of missing baryons. Fast radio bursts thus serve not only as astrophysical puzzles, but also as cosmological tools. Another avenue of study involves scattering and scintillation. Some bursts show broadened profiles or frequency-dependent structures caused by turbulence in intervening plasma. These effects carry information about both the host galaxy and the intergalactic medium. In some cases, bursts exhibit fine time structure indicating coherent emission processes and small-scale plasma features near the source. The brevity and intensity of fast radio bursts demand rapid response from observatories. Wide-field radio arrays such as CHIME in Canada and ASCAP in Australia have detected large numbers of bursts, while interferometers like the Very Large Array provide precise localizations. Multi-wavelength campaigns follow up in X-rays, optical and gamma rays to search for counterparts, though none besides the galactic event have yet been confirmed. The lack of consistent counterparts leaves room for multiple models and underscores the challenge of catching such brief phenomena. The connection between magnetars and fast radio bursts also ties into broader astrophysical processes. In the aftermath of a supernova, a young magnetar may be embedded in dense ejecta, providing both the engine and the environment for bursts. Over time, as the environment clears, bursts may weaken or cease. This could explain why repeating sources are associated with persistent radio emission that eventually fades. Some models also suggest that mergers producing magnetars could generate fast radio bursts linking them to gravitational wave events. Searches for bursts coincident with mergers have been conducted, though no definitive associations have yet been found. The variety of behaviors among fast radio bursts suggests that magnetars are a leading but not exclusive source. Other possibilities include neutron stars in binary systems, black hole interactions, or more exotic scenarios. The key evidence continues to point toward young, highly magnetized neutron stars as the most plausible explanation for many cases. The field remains young, with new bursts discovered almost daily, ensuring rapid progress. The scientific value of fast radio bursts extends beyond understanding their origin. They provide a new method for mapping matter between galaxies, measuring cosmic magnetism, and studying plasma physics under extreme conditions. Each burst is both a mystery and a probe, illuminating not only the nature of compact objects, but also the structure of the universe. The link to magnetars places fast radio bursts within the continuum of neutron star phenomena, alongside pulsars, glitches, and flares. Together they show how the extreme physics of compact remnants can produce signals across the electromagnetic spectrum, from gamma rays to radio waves, each revealing different aspects of dense matter and magnetic fields. As more data accumulate, the role of magnetars in generating these enigmatic bursts will become clearer, while the potential for other channels may also emerge. For now, fast radio bursts stand as one of the most exciting frontiers, their millisecond flashes carrying clues to both the engines that produce them and the vast spaces they traverse. Among the many classes of neutron stars, millisecond pulsars occupy a distinctive place because of their extremely rapid rotation and their extraordinary stability. These stars complete hundreds of rotations every second with spin periods as short as 1.5 milliseconds. Such rapid motion pushes the limits of matter under gravity, since the star must resist breaking apart under centrifugal force. Observations confirm that neutron stars can remain stable even at these extreme spin rates, offering constraints on the equation of state of dense matter. The origin of millisecond pulsars is tied to binary evolution. A neutron star formed in a supernova may initially rotate quickly, but gradually slows over millions of years as it loses energy. If later it acquires a companion that transfers matter through accretion, angular momentum from the infalling gas can spin the neutron star up again. This recycling process revives an old neutron star as a fast rotator. The accretion phase can last hundreds of millions of years, after which the companion may be reduced to a white dwarf or even completely evaporated by the pulsar's wind. The result is a solitary millisecond pulsar, or one in a binary with a low-mass companion. Evidence for this recycling scenario comes from accreting millisecond X-ray pulsar systems, in which accretion-powered pulsations are observed. These objects represent the transition between accreting neutron stars and radio millisecond pulsars. The discovery of such systems confirmed that spin-up through accretion is a real process and not only a theoretical idea. Measurements of spin frequencies across many pulsars also show a clear separation, with millisecond pulsars forming a distinct population. The stability of millisecond pulsars makes them valuable tools for precision timing. Their pulses arrive with such regularity that they rival atomic clocks. Timing measurements can detect variations as small as a few hundred nanoseconds. This precision allows tests of general relativity studies of binary dynamics and searches for gravitational waves. Pulsar timing arrays rely especially on millisecond pulsars, since their stability ensures that deviations in pulse arrival times can be attributed to external influences rather than intrinsic noise. The environments of millisecond pulsars also provide insight into binary evolution. Many are found in globular clusters, dense stellar systems where close encounters between stars are common. In such environments, exchange interactions can create new binary pairs, leading to efficient recycling of neutron stars. As a result, globular clusters contain disproportionately large numbers of millisecond pulsars. Observations in these clusters have revealed exotic systems, including pulsars orbiting other neutron stars or even planets. Some millisecond pulsars belong to categories known as black widow or redback systems. In these cases, the pulsar is accompanied by a very low mass star that is gradually ablated by the pulsar's wind and radiation. Material stripped from the companion forms eclipses of the pulsar signal, providing information about the interaction. These systems illustrate the extremes of binary evolution, where a neutron star can effectively consume its partner. The fastest known pulsars set limits on neutron star physics. If a pulsar spins too quickly, centrifugal forces at the equator would overcome gravity and disrupt the star. The maximum spin frequency depends on the equation of state, so observations of the fastest pulsars provide constraints. The current record holder spins at 716 times per second below the theoretical breakup limit, but close enough to challenge models. The absence of even faster pulsars suggests either a physical limit or evolutionary processes that prevent further spin-up. Another consequence of rapid rotation is enhanced emission of gravitational waves if the star has slight asymmetries. Even a tiny deformation in the crust could lead to continuous gravitational wave emission, detectable by sensitive instruments. Searches with LIGO and Virgo have placed upper limits on such signals, which in turn constrain how deformed neutron stars can be. If future detectors identify continuous waves from a millisecond pulsar, it would provide direct evidence of crustal mountains only centimeters high, but sufficient to radiate across the universe. Millisecond pulsars also serve as laboratories for relativistic dynamics in binaries. The first discovered binary pulsar, though not a millisecond pulsar, demonstrated orbital decay consistent with gravitational wave emission. Later discoveries of millisecond pulsars in tight orbits with white dwarfs or neutron stars allow even more precise tests. Measurements of Shapiro delay the extra time taken by signals as they pass through a companion's gravitational field, yield direct measurements of masses. Such observations refine understanding of neutron star mass distribution and constrain dense matter physics. The use of millisecond pulsars as cosmic clocks extends to navigation. Their predictable pulses can serve as natural beacons for spacecraft. Experiments with X-ray pulsar timing have shown that autonomous navigation is possible, using pulsars suggesting future applications for deep space missions. In this sense, millisecond pulsars are not only astrophysical objects but potential tools for human exploration. Population studies reveal that thousands of millisecond pulsars likely exist in the galaxy, though only a few hundred are currently known. Surveys continue to expand the catalogue, aided by sensitive radio arrays and gamma ray observations. The Fermi Gamma Ray Space Telescope has identified many new millisecond pulsars through their high-energy emission, later confirmed with radio observations. Each discovery adds to the statistical understanding of pulsar formation and evolution. The link between millisecond pulsars and fast radio bursts remains an area of speculation. While magnetars are leading candidates for fast radio bursts, some models explore whether rapidly rotating pulsars could contribute under certain conditions. So far, no definitive connection has been established, but the extreme stability of millisecond pulsars makes them less likely to produce irregular bursts compared with magnetars. Nevertheless, their role in the broader neutron star landscape remains central. The cooling behavior of millisecond pulsars is also of interest. Because they are old, their surfaces are generally cooler than those of young pulsars, yet some still emit detectable thermal X-rays. This emission may arise from residual heating by accretion or by friction between superfluid components inside the star. Observations of these faint signals provide indirect information about interior processes, complementing studies of younger and hotter neutron stars. Millisecond pulsars, through their rapid spins, stability, and binary histories, highlight the diversity of neutron star evolution. They are recycled remnants born again through accretion and transformed into clocks of unrivaled precision. Their presence in globular clusters reveals the role of stellar encounters in shaping populations. Their interactions with companions illustrate the extremes of binary dynamics. Their limits on spin and deformation constrain the physics of dense matter. In every respect, millisecond pulsars embody the intersection of stellar astrophysics, nuclear physics, and relativity. Each pulse that reaches Earth is not only a signal from a distant star, but also a measure of the stability of matter under the most intense conditions. The overall population of neutron stars observed across the galaxy reflects both the diversity of their manifestations and the limitations of current detection methods. Thousands have been identified as pulsars in radio X-rays or gamma rays, yet theoretical estimates suggest that hundreds of millions exist in the Milky Way. The discrepancy arises because only a fraction are oriented so that their beams sweep across Earth, and because many grow faint as they age and fall below detection thresholds. Catalogues of pulsars provide insight into their distribution ages and evolutionary pathways. Radio pulsar surveys conducted with large arrays such as Parkes, Arecibo, FAST, and KIME have discovered the majority of known pulsars. These surveys are biased toward objects with strong radio beams and toward regions of the sky accessible to the telescopes. As a result, many pulsars likely remain hidden in regions not yet covered or in populations too faint for current instruments. Gamma-ray surveys with Fermi have revealed pulsars invisible in radio, expanding the sample and showing that multi-wavelength approaches are essential. The distribution of neutron stars in the galaxy is not uniform. Most lie along the plane of the Milky Way, tracing the regions where massive stars were born. Their density is higher near spiral arms and lower in the galactic halo. Proper motion studies show that many neutron stars received significant natal kicks during supernova explosions, propelling them at hundreds of kilometers per second. These velocities scatter neutron stars away from their birthplaces, leading to a broad spread in galactic latitude, and in some cases ejecting stars entirely from the galaxy. Such high-speed stars are challenging to detect but represent an important part of the overall population. Population synthesis models attempt to account for these factors by simulating stellar evolution, supernova mechanisms, natal kicks, and observational selection. These models predict birth rates consistent with one neutron star formed every few decades in the galaxy, matching observed rates of supernovae. They also suggest that many neutron stars remain undetected because they no longer emit strong beams or because their emission is not aligned with Earth. These unseen stars may be detectable indirectly through gravitational lensing or through their effects on surrounding gas. Catalogues also reveal the diversity of neutron star types. Some appear as ordinary radio pulsars, others as millisecond pulsars, magnetars or central compact objects in supernova remnants. Central compact objects emit soft X-rays without pulsations and remain mysterious, possibly representing young neutron stars with unusual magnetic properties. Isolated neutron stars that emit only thermal radiation, sometimes called the Magnificent Seven, show surfaces, cooler than magnetars, but hotter than ordinary old pulsars, offering clues about thermal evolution. Each category fills in part of the evolutionary picture. Selection effects strongly shape the known sample. Radio pulsars must have beams intersecting Earth, and surveys are limited in sensitivity and sky coverage. Millisecond pulsars are often faint in radio, but bright in gamma rays, meaning gamma ray surveys discover them more efficiently. Magnetars are identified primarily through bursts, so many may go unnoticed if they remain quiescent. This means that current catalogues are incomplete representations of the underlying population. Improving completeness requires broader surveys and new instruments. The square-kilometre array now under development will dramatically expand sensitivity and sky coverage, potentially discovering tens of thousands of new pulsars. Space-based X-ray polarimeters and gamma-ray detectors will reveal magnetars and accreting neutron stars previously hidden. Gravitational wave detectors will provide complementary samples of binary systems. Together, these efforts aim to move from discovery of individuals to comprehensive population studies. Population statistics also constrain the physics of dense matter. For example, the discovery of pulsars with masses around 2 solar masses has ruled out soft equations of state. Further measurements of neutron star radii combined with population data will refine models of interior composition. The maximum observed spin frequencies of millisecond pulsars constrain crustal strength and stability. The fraction of pulsars in binaries informs supernova kick models. Each piece of demographic data connects to fundamental physics. The galactic distribution of neutron stars also influences searches for gravitational waves. Pulsar timing arrays require a network of millisecond pulsars distributed across the sky, and surveys continue to fill gaps to improve coverage. The likelihood of detecting gravitational waves from compact binaries depends on merger rates, which in turn are tied to neutron star populations. Understanding these populations therefore serves both observational astronomy and theoretical modelling. Beyond the Milky Way, neutron stars are harder to detect, but a few pulsars have been found in nearby galaxies such as the Magellanic Clouds. Fast radio bursts, if indeed linked to magnetars, offer a way to study neutron star populations in distant galaxies. By comparing rates and properties across environments, astronomers test how metallicity, star formation rate, and galactic structure influence neutron star birth and evolution. Cataloguing neutron stars also has practical applications. Pulsars are so precise in their timing that networks of them serve as galactic clocks useful for detecting gravitational waves and even for spacecraft navigation. Expanding the catalogue enhances these applications by providing more stable clocks across the sky. Each discovery is not only a new astrophysical object but also a potential tool. Despite the successes of surveys, uncertainties remain. The exact fraction of neutron stars that manifest as radio pulsars is unknown. The timescale over which pulsars remain visible is still debated depending on magnetic field decay and spin-down rates. The total number of magnetars, their lifetimes, and their contribution to high-energy transients remain under study. Even the birth mass distribution of neutron stars is not fully known. with some forming close to the Chandrasekhar limit and others exceeding 2 solar masses. Population studies are gradually narrowing these uncertainties. Continued monitoring of known pulsars adds another dimension. Long-term timing reveals changes in spin glitches and mode switching. These behaviors enrich the statistical picture, showing that individual stars evolve in complex ways. Combining these data with new discoveries builds a dynamic census that evolves with time. The unseen majority of neutron stars, those not detectable in current surveys, remind us that the catalogue is partial. Future instruments may reveal them through gravitational microlensing thermal emission at longer wavelengths, or indirect effects on nearby gas and dust. As detection methods diversify, the hidden population may become more accessible. For now, the known pulsars provide a window into the broader demographic, allowing inferences about the invisible remainder. The study of neutron star populations thus bridges the gap between individual case studies and galactic-scale understanding. It connects birth rates, lifetimes, velocities, and environments to the larger processes of stellar and galactic evolution. Each pulsar catalogued adds to a mosaic that, when complete, will show how the most extreme stellar remnants are born live and fade across the Milky Way and beyond.